October's sky is giving us a slow cinematic surprise, a quiet green traveler from the edge of the solar system that's waking up as it moves inward. It's not the roaring, headline-grabbing great comet that makes people drive an hour to watch it appear over a dark field. But it's the kind of celestial visitor that rewards patience, curiosity, and a pair of binoculars. Comet C, Arling Arwu Alil, Lemmon, discovered this year by survey telescopes at Mount Lemmon, has been brightening faster than many models predicted, developing the classic green coma that photographers and amateur astronomers love to chase. This is an event for both the eye and the lab notebook. An accessible spectacle for backyard skywatchers and a chance to test our ideas about how long-period comets respond to sunlight after millennia in the deep freeze. There's a subtle drama hidden in the comet's numbers. Long-period comets come from the distant Oort cloud, a vast, spherical reservoir surrounding the solar system where objects have spent billions of years in near-absolute cold. When gravitational nudges send one inward, the comet's surface, a mixture of ices, dust, and organic compounds, begins to sublimate, and the old nucleus wakes. For C 2025 A6 Lemmon, astronomers quickly recognize this story. A freshly arrived, long-period visitor that will sweep past Earth in October, warm toward perihelion in early November, and then recede back into the dark for many centuries. The specific orbital details are still being refined as more observations pour in. But the outline is clear. A rare, slow visitor whose behavior gives us a 2-month window for observations and discovery. One of the immediate and most visible signs of a comet's chemistry is color. The soft green halo that many observers have reported around Lemmon comes from diatomic carbon C and related molecules. When sunlight hits these molecules, they fluoresce, emitting light primarily in the green part of the spectrum, and that glow dominates the Comet's visual color. That green is more than pretty light. It's a direct chemical fingerprint. By studying the relative amounts of CCN and other emission features in the coma, astronomers can infer where a comet ESI size formed in the early solar nebula and how they have evolved during billions of years of interstellar cold. Observers photographing Lemmon have already noted a brightening green coma, evidence that solar heating is releasing fresh gases. Now, imagine tracking a living weather system in space. Comets aren't static. As the nucleus rotates and local regions become exposed to sunlight, jets of gas and dust can erupt, sometimes gently, sometimes violently. Those jets sculpt the coma and tail into knotted, braided patterns that change night to night. In Lemmon's case, recent high-resolution images show clumps, kinks, and short tail features that tell a story about localized outgassing and the physical texture of the surface. Each knot is a data point for thermal models: how quickly heat penetrates, which ices sublimate first, and whether the comet's interior is porous or compact. For everyone with a telescope, watching the night-to-night morphological evolution is the live drama of comet science. Science aside, the timing is almost cinematic. The comet's brightest window roughly coincides with the Orionid meteor shower peak and a dark new moon in mid to late October. That means observers under dark skies may be rewarded with two very different kinds of transient light. In the same night, swift streaks from meteors and the slow, graceful glow of a comet drifting west after sunset. For photographers, that's an irresistible composition: meteors streaking through a scene anchored by a faint green comet near the horizon. For backyard viewers, it's a reminder of how layered and connected the sky is. Different debris streams and icy bodies, all arriving from different parts of the solar system, telling overlapping stories. While Lemmon 1T likely become as dramatic as the great comets of the past, the ones that star in postcards and historical accounts, modest comets are scientifically rich. They help calibrate our expectations for how volatile materials behave when warmed after epochs in deep freeze. Early brightening, for instance, can signal volatile reservoirs nearer the surface than models assume. That early activity can mean the nucleus is losing material on short timescales, an important data point when we try to relate observed brightness to nucleus size and composition. When multiple telescopes watch the same comet over weeks and months, we can connect light curves to physics, rotational modulation, localized outbursts, and catastrophic fragmentation if the nucleus breaks apart. Those are the moments when amateur and professional observers collaborate best. Dense photometric coverage from backyard telescopes complements spectroscopy and high-resolution imaging from major facilities. Let's pull back for perspective. Comets like Lemmon are time capsules. Their ices and organics condensed in the cold, chemically diverse cloud around the infant sun. Studying the gases C, Cn, water vapor, CO, CO, and more lets us sample material frozen at the solar system's birth. When spacecraft like Rosetta studied 6-7P Curium of Gerasimenko up close, the community learned how porous and complex cometary nuclei can be. Ground-based observations of Lemmon combined with targeted spectroscopy can add new points to this comparative cometology. Over time, these comparative studies build a statistical map, which comets are rich in organics, which are dominated by more volatile ices, and how formation region relates to present behavior. That map, in turn, shapes big questions. How much water could comets have delivered to early Earth? How did organic chemistry assemble in small, icy bodies? And we aren't watching Lemmon alone. The sky in late October 2025 is busy. C 2025 R2 Swan and the highly watched interstellar visitor 3I Atlas are nearby en route through the inner system. That simultaneity is valuable. When different comets, one local, one interstellar, are observed under similar solar conditions, scientists can conduct coordinated campaigns to compare outgassing behaviors, dust production rates, and tail morphologies. That, as a rare natural experiment, 2 or 3 different icy bodies facing the same heating and radiative environment, but carrying different chemical histories. Observatories worldwide are scheduling time to capture these objects simultaneously, yielding datasets that wouldn't exist in isolation. For amateur observers and astrophotographers who want to catch Lemmon, practical tips matter. The comet spends much of its October apparition low in the western sky after sunset, and will generally sit under 20 altitude from many northern hemisphere locations at dusk. So a clear western horizon is essential. Binoculars will show a faint, diffuse patch to many observers under dark skies. A small telescope 4 to 8 inches will reveal a defined coma and short tail if the sky is steady. For photographers, wide-field lenses and short exposures can capture the comet's color and position. Stacking multiple exposures across the night can reveal tail details while avoiding overexposure from background stars. Use apps such as Stellarium or the SkyLive and local astronomy club updates for precise nightly coordinates. You want to get scientific value from your images? A few simple steps make your observations more useful to pros. Log the exact UTC time of each exposure, include the focal length and exposure details, and retain the raw files if possible. Amateur images with good metadata are often used for photometry, measuring the comet's brightness, and for documenting morphological changes. Community databases like the Comet Observation Database and collaborative comet monitoring groups welcome such submissions. And in many cases, amateurs have been the first to detect fresh outbursts. Don't underestimate the value of consistent nightly imaging. Comets change gradually, and a steady amateur record is sometimes the only continuous dataset available. On the professional side, spectroscopic and photometric monitoring is underway. Large facilities from Gemini to Hubble are targeting the comet to measure molecular abundances and search for unusual isotopic ratios. Interstellar 3I Atlas, in particular, has produced surprising spectral hints, including an unusual nickel-to-iron ratio in early NEPs. Observations that have sparked extra interest in how different origins produce different cometary chemistries. While Lemmon is a solar system resident, Comparing its spectrum and dust properties with those of the interstellar visitor promises new constraints on how common various chemical pathways are in other star systems. Multi-wavelength observations, optical, infrared, even radio paint the most complete picture. Dust production and scattering are best caught visually and in near-infrared, while gas species and isotopes sometimes require spectrographs and radio receivers. A word on safety and scale. Comets like Lemmon are marvels, not threats. Their paths are tracked by professional orbit determination teams, and current solutions place Lemmon safely far from Earth. The scientific value of observing it lies in what the comet can teach us about physics and chemistry across time, not in any hazard it might pose. Instead, count it as a once-in-many-lifetimes chance to see a body that won't return for millennia. Plan your observing nights, find a clear horizon, and treat the experience like an archaeological dig in slow motion. Each photograph and spectrum digs into history. Image, comparative historical image of a great comet, Hale-Bopp. To give viewers context for what a great comet looks like versus a modest but scientifically rich visitor like Lemmon. Credit: NASA Public Archives. If you're making video content, structure your piece around 3 acts: discovery and context. Tell the origin story of the discovery at Mount Lemmon and why long-period comets matter. The live view give practical what-to-watch tips, show maps, and current images, and the science explain fluorescence, outgassing, and what coordinated observations can reveal. Close with the human angle. How centuries before our telescopes, humans would have watched a faint patch cross the sky and then never seen it again in their lifetimes. A reminder that some celestial events are truly generational. Insert the sequence of images and maps in the moments described above. Discovery photo early on, close-up coma in the middle, sky map at the observing tips. Comparative historical photo near the end. The images I've placed in this script correspond to well-documented, citable sources you can use directly. Before I finish, 3 small caveats that matter scientifically and for viewers. First, comet brightness predictions are notoriously unreliable. Small changes in surface composition or the exposure of a fresh, volatile pocket can suddenly change a light curve. Second, orbital solutions refine as more data arrive. Astronomers update perihelion times, perihelion distances, and close approach distances. Use official observing resources for the latest numbers. Third, morphological features, jets, knots, and tail splittings can appear and evolve rapidly. They often require good seeing conditions and tracking to reveal. Expect surprises and celebrate the fact that comets still delight us by being unpredictable.